So hello everyone. Thanks for joining us today. My name is Queenie. I work at PingCap. It's our great honor to have Dr. Manuel Rigger from ETH Zurich to talk about finding logic bugs in database management systems. We all know Dr. Manuel from his great work in the TiDB Bug Hunting Challenge program, where he has won over 100 t-shirts by finding 22 P1 bugs and 6 P2 bugs magically. He will reveal all the secrets behind the magic today. What's more, Dr. Manuel will also cover SQLancer, the new and hottest open source project in database testing area. Today, we also have 3 guests from PingCap for panel discussions. Xiang Zhou, he is our team leader of the infrastructure tools team. Zhong Yiguan, he is our software engineer in testing. Huaiyu Xu, he is our developer in TiDB SQL engine. Today's meetup will last for about 1 hour and 10 minutes, including a talk from Mr. Manuel and 3 panel discussions about different approaches Dr. Manuel has adopted in automatic testing. Without further ado, Mr. Manuel, please start your talk. Thank you.
Thanks a lot, Queenie, for the very nice and generous introduction. So as Queenie said, my name is Manuel, so just feel free to call me Manuel. And I'm a postdoc at ETH Zurich, working on testing database management systems, which is work that I've been doing together with Professor Chano Su, who leads the Advanced Software Technologies Lab there. So the goal of our work has been to find logic bugs in database management systems, which poses immediately the first question, namely what are logic bugs? So let's assume that we have a query like the following. And please note here that in order to denote a Boolean predicate, I will always use a phi symbol. Let's assume that we send this to the database management system. And let's also assume that we have a database with 3 records. And the database management system is expected to go over all the relevant records, see where the predicate evaluates to true, which is here for 2 cases, and then return a result set containing all predicates, all rows where the predicate evaluates to true. So this is the expected behavior. But for logic bugs, it can happen that the database management system returns an incorrect result set. A concrete example is here, where only row 1 is fetched, although row 1 and row 2 should have been fetched. Another example is that a row is mistakenly omitted. The contents that is fetched here is incorrect. Now we believe that logic bugs are quite serious. For one reason is because they might go unnoticed, both by users and by developers of a database management system, because it's not obvious when they happen. This is unlike, for example, crash bugs. So you can imagine that it might happen if you trigger a memory error or an internal error in the database management system, and this is easily detectable by users. Now, isn't the problem already solved? Because if we look out, then we can see that actually a couple of database management systems have been developed and maintained for over 20 years. And I want to give you just one example on one testing process of a database management system, namely the one of SQLite, which has been developed for over 20 years. And they documented their testing effort as follows. So they basically published that they have 700 times as much test code as they have source code, which is already quite an impressive number. They also achieve 100% branch test coverage. Even more, they achieve 100% MCDC coverage, which is a stricter coverage metric than branch test coverage, and actually often used in the aviation industry to give certain guarantees. Also, it's extensively fast, for example, by Google's Open Source Plus project, and also by individual researchers. And besides more, let's call it normal testing, like unit testing, integration testing, they also have, for example, anomaly testing where they verify that the database management system works correctly in the presence of out-of-memory errors, input errors, and power failures. So this is only one example of such a testing like process or technology that they use. but it shows that database management systems in general are really well tested. Nevertheless, we have found over 400 in popular and widely used database management systems, including but not limited to TiDB, also SQLite, which I just mentioned, MariaDB, CockroachDB, MySQL, Postgres, and DuckDB. So quite a number. As Queenie also mentioned initially, we have won this bug hunting challenge where we reported 22 bugs that were classified as P1 bugs and also some as P2 bugs. And as Queenie said, I'm also looking forward to the t-shirts that I will be able to redeem. So what are the ingredients of an effective automatic testing approach, specifically in our context of testing database management systems? Well, the first thing that we need is we need to have an effective test case. That means we need a database and a query that can stress the database management system and potentially expose a bug in it. And the second component or ingredient is that we need a test oracle that can validate whether the query's result is correct or incorrect. Now, query and database generation are actually the simpler part of the problem, I would argue, and thus they're not the focus of this talk. Nevertheless, I want to shortly mention how we generate databases and queries based on which we test the database management system. So specifically, we have two phases which we use to generate databases. In the first phase, we randomly generate tables. So you can see here that we generate two tables, T0 and T1. And for this and other statements, we actually have some lower and upper limits that specify how many of them can be, how many of them can be generated, and also the user might modify those. And after we created tables, we randomly select other actions. So for example, here insert to insert data, to update data, to create indexes. And what I also want to note here is that statements can actually fail or be redundant. So this insert here inserts the value 0 twice, as you can see. And since this table or this column here has a unique constraint, this statement will actually fail. What I basically want to say is that our process of how we generate databases is actually quite easy and quite naive. So it works like this. Similar for query generation, the core challenge in query generation is to come up with random expressions where we also select applicable options randomly. So for example, here you might imagine that randomly the is not operator is first chosen. And since the is not operator needs two operands, these are also randomly generated. And here we have a column reference and also an integer. As I said, the focus of the talk are not how we generate databases and queries, but how we actually come up with test oracles that can effectively find logic bugs. What's a test oracle? A test oracle for a given input determines whether the system works as expected. So in our case, the input would correspond to the query and the database, and we want to test whether the output is as expected. Now, what approaches would be applicable to test database management systems in this regard? So probably many of you have heard of fuzzing tools like SQLsmith, and these and other random query generators, they generate queries, which are then sent to the database management system in the hope to trigger, for example, a memory error that then causes a segmentation fault in the process to exit. So here the test oracle is basically that we test, for example, for a non-zero exit code. But this, of course, doesn't help us for finding logic bugs, because for these the result is incorrect. Now the idea is why we cannot just take this random query generator, generate one query, and send it to multiple database management systems. So for example, we might send it to MySQL, TiDB, and SQLite. Each of which would then return a result that we could then compare against each other. If all the result sets are the same, then we suspect that the database management system might work correctly for this test case. Otherwise, we can infer that at least one of the database management system is buggy. technique is not new. It has been proposed by Microsoft Research in around 2000 in a system called Rex. And the author stated that it was extremely useful since they could actually find a number of bugs. But they also stated that this is only applicable for the small set of common SQL. And this is also our observation. So basically, the problem is that the common SQL core is actually rather small because all database management systems either have extensions to the standard or they implement some features in a different way. But this is also, for example, validated by companies. So, for example, Cockroach Labs, they posted a blog post stating that they cannot use they cannot use Postgres as a test oracle to compare against CockroachDB because both systems have slightly different semantics. Now, another interesting reason is also that differential testing cannot establish a ground truth. That could mean that when we use differential testing to, for example, compare MySQL against TiDB, there might happen that both have the same underlying bug, which is also noted here by the TiDB developer. And this is actually also what we saw with other database management systems as well, that they share common bugs. Now, besides fuzzing and differential testing, what we could also consider is other approaches that have been proposed. So, for example, some researchers had the idea to use solfuzz. So besides fuzzing and differential testing, also other potential testing approaches exist. So I just mentioned the solver-based one, where we believe that solvers do not have a high enough throughput to find that many bugs. Then also approaches for performance testing and also to test the cost estimation of the query planner have been proposed. However, it's unclear how they could be extended to also test for logic bugs. So overall, we have to conclude that the problem of testing database management systems to find logic bugs has not yet been well addressed. And this is where our work comes in. So we have been working on 3 testing approaches to finding logic bugs, namely PQS, non-optimizing reference engine construction, NOREC, and Ternary Logic, query partitioning, TLB. So pivoted query synthesis is a general technique where the idea is that we want to generate a query that is guaranteed to fetch a randomly selected row to which we refer as the pivot row. And this technique allowed us to find about 100 bugs. Non-optimizing reference engine construction on NOREC has the main idea that we want to generate an optimized query that we then translate to a so-called unoptimized query. And by detecting or by checking their result sets, comparing against each other, we can detect bugs in the query optimizer. And finally, the idea of TLB is that we partition a given original query into original query into so-called partitioning queries, each of which computes a partition of the result that we can then use to compare against the original result set. As Queenie mentioned initially, we have implemented these approaches in a tool called SQLanswer, which since last week is available on GitHub. So please feel free to check it out and give us feedback or use it. I also want to highlight that Jan and his team have been working on GoSQLanswer, which also supports all 3 approaches and has been specifically implemented by them to test TiDB. So please also check it out. And with that, I want to start with the first, with describing the first approach. And actually, also before I forget, after each approach that I'm going to present, we have a short round of discussions and questions before we resume with the next testing approach. So please feel free to ask any questions then. The goal of NOREC, of non-optimizing reference engine construction, was that we have an easy to realize technique. So easy both in terms of implementation effort and knowledge required to understand the technique. That can find bugs in the query optimizer specifically. what are optimization bugs? Well, we can assume basically the initial motivating example and also assume that the bug affect the query optimizer. Now, if we look what compilers provide, like GCC and LVM, we can see that we have some flags like O3, which enables all optimizations, and O0, which disables most of them. Now, it would be perfect if we would have something like this for database management systems, because then we could send a given query to the database management system, once to the optimizing version and once to the version that doesn't optimize. And then if the query optimizer is affected by a bug, then it would be expected that both return different result sets that we could then detect. Now, while investigating various database management systems, we actually found that they provide limited control over optimizations. So every database management system offers some options to disable or enable some optimizations. They do not, in general, offer a comprehensive way to, for example, disable indexes. Now, the idea that we had was why, like we do not necessarily have to rely on the database management system to disable optimizations. What we could do alternatively is we take the query and rewrite it in a way so the database management system cannot optimize it. Basically, the idea would be illustrated here. We would have a query generator that generates an optimized query. Actually, we call it optimized query, but it might not actually be the case that it's optimized, but the structure at least would enable the query optimizer to optimize it. Now, this optimized query would potentially trigger the bug in this query optimizer, and here only fetch a single row. And the idea would then be that we have a translation step that derives an unoptimized query from this optimized query that doesn't or is less applicable by optimizations and returns the correct result, which would then be enabled to us to detect the bug in the query optimizer by comparing the two result sets. So I guess while the approach sounds plausible to you in principle, it's not obvious how the translation step would look like. And this is actually the core insight of our approach. Before explaining it in detail, I also want to mention shortly that in the subsequent slides, you will see that we only check the number of rows, but actually we could also use this technique to compare the contents of the result sets, but we found this is actually not often a source of bugs. So the majority of bugs we can detect only by counting the rows. So first we generate this optimized query, which has this general structure, basically selecting all records from some tables where the predicate holds. And then if the query optimizer is affected by a bug, then it would be expected that both return different result sets that we could then predict. Sorry, I was just distracted by some echo. So basically in this example here, two rows would be fetched, namely the two where the predicate evaluates to true. Now for the unoptimized query, all we have to do is we have to take the predicate from the work clause and move it directly after the select. Now what is the result of this query then? It basically means that this Boolean predicate is evaluated on every row in the tables here. So basically the cross product of the tables, cross product of the rows, meaning that a true value here is contained every time the predicate evaluates to true for the given row and otherwise false. So here you can see that we have 2 times true contained in the result set and 1 times false. And from this we can basically judge that predicate phi evaluated to true for 2 rows. This is the expected behavior, but if now the query optimizer is affected by a bug, then it's very likely that the first optimized query results in an incorrect result set, but the unoptimized query still works as expected. Now the insight here again is that the first optimized query contains simply the original rows and we count them. And for the unoptimized query, we count how often who it's contained in the result set, because the result set contains both true and false values depending on to which Boolean value the predicate evaluates. And the insight why this approach worked in practice is that we found that most optimizations reduce or aim to reduce the amount of data that is processed. For example, they use indexes to speed up the query processing, which are applicable here or potentially applicable. But for this unoptimized query, the database management system has to go and fetch all the rows in the database anyway. So the predicate also must be evaluated on every row, which makes many optimizations, including indexes, inapplicable. So in summary, the translated query cannot be efficiently optimized by the database management system. How can we implement this effectively? Well, there is one insight that we can use aggregate functions to do this. So for the optimized query, we can use a count aggregate function, which here in its incorrect case would return only a single row with the value 1. An unoptimized query here sums up how often the predicate evaluates to true, in which case here the whole expression evaluates to 1, which is then summed up. If it evaluates to false or null, then it will evaluate to 0 and not contribute to the sum. And here in the correct example, 2 would be returned, which would allow us to detect this bug. Now I want to give you a concrete example of a bug that we found in SQLite. So you can see here that we create a table, we insert some values. You can also see here that we have this optimized query with the predicate that involves a regular expression. And I think the beauty about this technique is that we actually do not need to reason what the result of the query should be. All we need to do is we send it to SQLite, which in this case here returns an empty result set. And in the second case here, we pass the unoptimized query to SQLite, which returned a single row with the value true. And based on this value true, we can actually infer that the row should have contained one row for the optimized query. We could detect this as a bug. So in total, we have found 160 bugs in database management systems, many of which have been already fixed. So in this specific example, we evaluated our approach on SQLite, MariaDB, Postgres, and CockroachDB. What I want to mention here is that you can see we found most bugs in SQLite, but the reason for this is that we focused our testing efforts on this database management system. So we also implemented, for example, some extensions in our testing approach to comprehensively test this DBMS. Now, 1/3 of the bugs that we found were optimization bugs. The other ones were error and crash bugs. And it seems that these are either more common or easier to find. So we do not really know which one of these is true because we don't have a ground truth on all the bugs. So, and with that, I think the first discussion round starts. So looking forward to your comments and questions.
I have a question here. Can you hear me, Manuel?
Oh yeah, I can hear you.
Oh yeah. As you mentioned, NoRack mostly concentrates on testing logical bugs caused by optimization on the where clause. Is that right?
Yes, that's correct. Yeah.
Okay, sorry. Can you see from the
yes.
chat panel?
Yeah. Yes. So the question from Huaiyu is: do you have any idea to test the logical bugs caused by the optimization rules which are irrelevant to the where clause?
That's a very good question. So we had exactly the same concern or idea that a NoRack is basically only applicable to testing the where clause. But in the approach that I'm going to present next, TLB, we actually try to generalize the idea or come up with an approach that is also applicable to testing other features like having clauses, aggregate functions, and so on. So that's basically something that I'm going to discuss in the next approach. So thank you for the question.
Thank you, Huaiyu. Any other question from?
Hi, Manuel. Can you hear me?
Oh yeah, I can hear.
Okay. I have some questions. The first one is the expression in real clause. Is it required to be evoked as true or as boolean, or it can be some number or other things?
That's also a good question. So it actually depends on the database management system, because some database management systems like TiDB actually have some implicit casts where there is a conversion, an automatic conversion to Boolean. But for some other database management systems, like for example Postgres, they actually have a stricter type system where we need to explicitly convert it to a Boolean. But like you said, it's also, for example, possible for many database management systems to just use a number in the word clause, and it will be automatically converted to a Boolean.
Okay. So in the counting implementation, I say we put the unoptimization version to a subquery and sum it if the expression is a number, so the sum of it might not be a count of the optimization version. Does it true?
Like I'm not completely sure if I understood you. I either mean that the counting doesn't work because it's a number then, or?
Yeah.
I see. So it's basically what we need is we need to have explicit it's true clause. Maybe I can read it on the complete slide. So you can see here that we have this explicit version, and if it's, for example, a number like 5 and 5 is true, it will quickly into a Boolean.
Okay.
But as you pointed out, actually, it should also be mentioned here that depending on the database management system, this period might look a little bit different. So, for example, for some database management systems like Postgres, we need to have some explicit cast here to an integer.
Okay. I see. I have another question. We also developed some fuzzing current generator, but we found that most of the currents that generated are complex and it's difficult to read. And I see the paper you have some. You have a circle specific reducer. Can you explain how it works?
Yeah, that's also a very good question. So as you mentioned, also all the examples that I'm showing, they are all reduced cases, basically where we took a tool like cReduce. So cReduce is actually written specifically to reduce C code, but actually it also has a number of more general purpose passes which work reasonably well for SQL as well. And at the beginning we have been using this, and also afterwards we manually reduced the test cases. But now actually a student, Jonas Winterner, he has been working on a reducer specifically for SQL code, and I hope we will also release this tool soon to profit for the community.
Okay. Yes, thank you.
Okay, there is a question from YE. I wonder which version of DBMS you find the bug with this approach. In which version the bug is fixed? Yes.
That's a good question. So it depends on the database management system under test. So here I want to again highlight the SQLite developers. They actually were very responsive and typically fixed our bugs, and even almost on the same day as we reported them, which is why we could find so many of them. And there we always tested the latest development version. Yeah, actually, for all the database management systems, we always use the latest development version. The exact versions where the bugs were fixed, it's I don't remember. I would need to look up the statistics. But in general, most of the bugs were fixed in the latest development version while we were testing them.
Okay. Then there is another question. Is there any technique, any method to detect in the storage layer?
That's a very good question. So I believe that it would be a very interesting idea to try also find bugs in this layer. But now for the moment, we have been only working on detecting logic bugs directly. So we're basically, our goal was to always find when a query returns an incorrect result. But I also want to mention that actually we can also find bugs in the storage layer in that sense that we found a number of bugs that were related to indexes, for example, where the table contained different records than were contained in the index, which is related to the storage layer, I think.
Okay, to this question, I have something in mind. In PinCab, we developed a chaos mesh that chaos mesh can test the storage layer, but with photo injection. I think the upper, if there are many factors in the upper and the button is the chaos mesh, maybe we can detect some bug in storage layer. Yes, I have a question about the rack too. What if the original implementation has bug? So the non-optimizer has bug, and so how can we detect it?
Right, that's also a very good question. So the first two approaches that I'm going to present today in the talk, they have the limitation that they can only detect bugs where the database management system behaves inconsistently. But the last approach that I'm going to present can also provide a certain kind of a ground truth where we can detect such bugs. So for a no-rec and also for TiDB, they're actually quite restricted in the kind of bugs that they can find. And we wanted to address this also with the last approach that I'm going to present today.
Okay, thank you. I got it.
Yeah, thank you for your questions and comments. Now, please move on to the Ternary Logic query partitioning, the TLT approach. Thank you.
Okay, sounds good. Thank you for your valuable questions and input. So Ternary Logic partitioning, TLP, as I said, the element that we faced was that no-rec is mostly limited to testing work clauses, but we also wanted to test other features such as aggregate functions, having clauses, group by clauses, distinct queries, and so on. So in order to come up with ternary logic partitioning, we actually first came up with a more general idea or technique of query partitioning. And the idea is that we have a random query generator that generates a query queue. And basically, queue means or corresponds to the original query. We can also see here that we use this circle to denote a result set. And based on its original query, we want to derive other queries, each of which computes a part of the result set. And then the idea is that we have some operator that can combine these partitions to yield a new result set. And the assumption is that these two result sets would be the same. Now, if that's the case, then the database management system seems to work correctly, but also, again, with the limitation that we can only detect cases where the database management system behaves inconsistently. And if there is a discrepancy, then we can detect it as a bug. Now, for terminology, these derived queries, we refer to them as the partitioning queries, and they compute partitions, which are parts that are then composed to the new result set using this composition operator, which is denoted with this diamond symbol here. Now, I guess the approach sounds possible in principle, but it's not obvious again how to realize it. Namely, the challenge is here that we can come up with a partitioning strategy that can stress the database management system in different ways. And there we had the following insight to realize it. So let's assume that we have some predicate phi and some row r, And exactly one of the following must hold. Phi evaluates to true, not phi evaluates to true, or phi is null. So SQL is a ternary, or uses a ternary Boolean logic, which means that a predicate can either evaluate to true, to false, or to null. And we can use this insight to partition some given result set here to three partitions using this non-negated version, the negated version, and the is null version of the predicate. And these three predicates are called the ternary predicate variants. So it was perhaps a bit abstract, which is why I want to give a concrete example next, namely of a bug that we found in MySQL. You can see here that we have two tables, T0 and T1, with each of which has a value stored, namely here 0 and here -0. And when we reported the bug, we reported the following test case, where we fetched all values from T0 and T1, where these two values here of the columns evaluate to the same value. Now, unexpectedly, MySQL didn't fetch any rows, which is unexpected because 0 should be equals to -0. The question is now, how did we find this bug using TiDB? Basically, what we did is we randomly generated this original query that simply fetches all records from T0 and T1, so the cross product of records. And here, MySQL is expected to process the query correctly, and indeed, a single row was fetched as expected. Now, based on this original query, we then derived the partitioning queries. You can see we have three queries, one with the randomly generated non-negated version of the predicate, with the negated one, and then the is null version of it. And unexpectedly, for this query here, MySQL didn't fetch any rows. Since we would have expected that these two result sets are the same, we could reduce the bug and also report it as shown on the previous slide. Again, how does this illustrate to our initial idea? Well, basically, Q corresponds in the example to simply fetching the cross product of rows from T0 and T1. We had three partitioning queries with the non-negated version, with the negated version, and the is null version of it. And perhaps you spotted it on the previous page. To implement the composition operator, we used union all, which combines the result sets without filtering out duplicate values. So now I demonstrated how this technique works for work clauses, but actually we set off to find bugs in other features such as group by clauses, having clauses, listing queries, and so on. So the question is, how can the approach be generalized to also find bugs in this feature? Well, in order to explain this, I want to use this table-like format here, where in the first column we have the original query. Here in the middle column we have the partitioning query, and you can see here that each partitioning query is instantiated with a version of the ternary predicate variant. And in the last column here, we have the implementation of the composition operator. Now this symbol here corresponds to the multi-set addition, and in SQL it basically means union all. So this is the specification for the work clauses that we already have seen in action. In order to test having clauses, all we need to do is we need to apply directly the same approach, but this time we use the ternary predicate variants in the having clause rather than in the work clause. For testing distinct clauses, the original query contains the distinct keyword, and the partitioning queries can either decide to also use it or to omit it, because here the insight is that the composition operator is implemented differently. In here we use the set union, which in SQL is implemented using this union keyword rather than union all, which is the multi-set addition. And this helps us filtering out these duplicate values. In order to do group by clauses, it looks quite similar to work clauses, but here we need to be careful that the columns that are fetched should also be contained in the group by clause, because again we use this union to filter out duplicate values, so all the columns must be contained here also in the goodbye clause. Now, more interestingly, aggregate functions. For aggregate functions, we have an individual test oracle for each aggregate function that we want to test. Perhaps the simplest test oracle is for the max and min functions, which compute the maximum and minimum values. You can see that the original and partitioning queries look like as we would expect. But the composition operator here is more interesting. Specifically, while for the other test oracles, a partition always corresponded to a subset of the result set, here a partition is actually the intermediate result computed so far. So for the maximum value, this means that each partition corresponds to the maximum value computed for the rows that are selected by the respective partitioning query. And then we need also an outer aggregate function to compute the overall result. I guess this is also best explained on a concrete example of a bug that we found here in CockroachDB. You can see here we have two tables, and we also insert some values into them. Now, for the original query, we simply used max here on the row ID column, and CockroachDB returned a single row with the value null. And now for this partitioning queries, you can see again that we have the ternary predicate variance. You can also see that we use this max to compute the partition. And importantly, here we use this outer max function to compute the overall result. And here CockroachDB computed an incorrect or inconsistent result, which allowed us to detect this bug. It also, like what I've demonstrated on the previous slide, are so-called self-decomposable aggregate functions. I don't want to explain the formal background of this, but I want to mention that there's also a category of decomposable but not self-decomposable aggregate functions. And I guess it gets clear on the example what this means. Specifically, if you think about, for example, the average function, then it's insufficient if we only use a single value as the result of a partition, because we need to know how many values the average actually is computed over. So rather than using a single value, we use a tuple being the sum of the expressions and also the count. And based on the sum and count, we can then compute the overall average in the composition operator. Now, there also exists a category of aggregate functions that are called non-decomposable, which would be even more complicated to test, like group concat, where the ordering of the strings that are concatenated is relevant, but I don't want to go into detail about this, and we actually didn't try to test those because we believe that since they are more difficult for us to test, that they are also more difficult to optimize. So using this technique, we have found close to 200 bugs, many of which have been fixed. And here I want to mention also that this is the approach on which we evaluated TiDB. Again, what I want to stress is that the total number of bugs reflects our testing effort and not actually how robust the respective database management system is. Well, let's look a little bit closer what this oracle allowed us to find these bugs. You can see here that the Were oracle found the majority of bugs. So it's not only the simplest, but also the most effective test oracle in this or of this approach here. The other more advanced oracles found interesting bugs, but in total they found a lower number of them. We also wanted to stress that we implemented these additional oracles only for database management systems for which our bug finding efforts saturated. So for some, we couldn't proceed testing because we still found a number of bugs with the Were oracle. And actually, it's also easy, or it can happen. A number of bugs are found, for example, by the having test oracle. They're also found by the Were oracle, simply because the having oracle also generates Were clauses. Now, how does this new approach compare with the one I showed initially? Well, the new approach allowed us to test additional features such as aggregate functions. Also, it allowed us to find bugs in union and union all, which is used to implement the composition operator. And finally, we could use this approach to find bugs in the unoptimized version of joins and operators. And no-rec, on the other hand, I mean, first of all, it's probably simpler to implement, but it can also find bugs in the unoptimized version of query, namely in the version where an and couldn't be detected. And we think we start casting this option and
He asked how to make your test data, how to make sure that Slutz is large enough to find.
Yeah, that's a very good question. So actually, what we have been doing in our process is we've always created a very low number of rows and potential. The insights that first of all, it reduced bugs we found. Not much data is needed, and also that makes fuzzing or testing much more efficient because we can issue many more queries in a certain time span than if we have a larger table. But we are aware that actually we might omit bugs, like finding bugs that are only triggered using more records, a larger table, and so we can also, or the database system can efficiently execute it. So,
Hey Manuel, can you hear me?
oh yeah, I hear.
I have a question about Ternary Logic partitioning. Have you tried compress aggregate expressions in select clause? We now know the simple aggregate functions like sum, max, and min is a self-decomposition. Self-decomposable. Yeah. Have you tried the more complex expressions?
Actually not so. As I said, in our work, we only tried to find bugs in the most common aggregates, and we haven't really thought about how we can test more complex ones. So there would be, like I mentioned as an example, this group content function, and I think we could, for example, test this by, in the test oracle, also splitting the strings again and then comparing the test result without paying attention to the order. But that's somehow unsatisfactory because the testing effort then all grows, and I assume that it would be made similar with testing compressed and uncompressed. So I guess this approach, it's not immediately clear how it could be applied to this advanced aggregate functions. You're right with that.
The other fuzz approaches can help to detect logical bugs. Do you have any idea?
So I'm actually not really familiar with much other work that has effectively found the kind of bugs that we are trying to find. I mean, I know that, for example, if you want to test for transaction-related bugs, Jefferson, I guess, is the best or the only choice. So I'm aware of this, and of course, many query generators that you can use. But actually, for logic bugs, I think the state of the art is simply to use good unit testing and integration testing, which requires much more effort. Do you know of any others?
Oh, I don't know. For transaction tests, I don't know any others. Yes.
I see. Okay. Thanks.
Okay.
Hi, Manuel. Can you hear me? I have a question. This is from Kerry Wang, and my question may not related to SQL itself. I have interest in your data generator framework. So as you do so many tests, do you need to generate massive of data, dummy data? And what is the principle or concept for generating those data? Because if I can know how does it work, I can apply it to generating some unit test data and integrity test data and so on.
I see. Yeah, thank you for your question. So, as I shortly mentioned before, actually, the main consideration for this part has been so far that it executes efficiently. So we have only been generating very little input data for the tables, because this basically allows us to issue many, and the database management system can basically immediately come back with the result. And the majority of bugs that we reported, they can actually be reduced with only very few rows. So many examples, even one row is sufficient to reproduce the bug.
Okay, thank you.
Okay, thanks.
Thank you, Kei. So we also...
So I think the most commonly fuzzer is is a sequence, which is also available on GitHub. One work that sounds very interesting is by researchers from Georgia Tech. They have been developing a tool that's called a Squirrel, and they've recently also released their code on GitHub. And as far as I know, they have found quite a number of crash bugs also in widely used database management systems. So I guess that's the latest and probably the strongest fuzzing approach. So maybe you would like to check this out. It's called the Squirrel.
So thank you, Manuel, and thanks, Jim Hongman, for the question. So let's move on to the next approach, which is pivoted query synthesis, PQS.
Yes, thank you for your great question. So for the next approach, as was pointed out previously, a limitation is that we cannot give any ground truth. This is an inherent limitation of so-called metamorphic testing approaches. So both NoRec and TLB are metamorphic testing approaches. And in this context, this means that we have a SQL query that we execute and then get a result set. And based on this query and the result set, we derive a new SQL query, and the test oracle that can decide whether the system works as expected. Well, and it's a fundamental inherent limitation of metamorphic approaches that they cannot establish a ground truth. They can only detect cases where the database management system works inconsistently. Now, in order to address this, we came up with a PQS, where the idea was to come up with a divide and conquer approach for testing database management systems and also provide a ground truth. As a side note, this is actually the first approach that we have come up with, but it's a quite powerful one in terms of what bugs it can find. The core idea is that we want to come up with a testing approach that only considers a single row at a time, and we refer to this row as the pivot row. Now we tackle two challenges in the testing process. First, we generate a meaningful query. It's meaningful because it's guaranteed that the query will fetch at least one row, which is the pivot row, and potentially also some other rows. Furthermore, we tackle the test oracle problem in the sense that we can validate that the pivot row is indeed contained in the result set. If not, we have found a bug in the database management system. So why do we focus on only a single row at a time? Well, first of all, we thought that it would be simpler, both implementation-wise and also conceptually, when considering, for example, all rows in a database or table. And we also thought that we could achieve a similar effectiveness as checking all rows, because you can imagine that we start verifying with one row, and then we go on with another one until many or even all of the rows have been checked for the respective query. How does the approach work? Well, first we randomly generate databases as for the other approaches. Then we select a pivot row. We generate a query that is guaranteed to fetch the pivot row. And finally, we verify that the pivot row is indeed contained in the result. When we can repeat the process just by either going back and generate a new query that fetches the pivot row, we can select a new pivot row, or we randomly generate a new database. Now, before going a little bit more into detail in the approach, I just want to illustrate how this approach allowed us to find a bug in SQLite. So you can see here that we create a table, we create an index, we insert some values in the table, and what we then do is we need to select a pivot row. I'm selecting here null because this is actually the only row that enables to trigger the bug here, or at least enable detecting the bug. Now, based on this pivot row, we generate a query that is guaranteed to fetch the pivot row. So in this example, we could, for example, generate that the value of this column is not 1. Since null is not 1, this should evaluate to true. We send this query to SQLite, which fetched 3 rows. Surprisingly, the pivot row was not contained in the result set, and this actually allowed us to find and report this bug to the SQLite developers. Now, the core question is, of course, how can we generate a query that is guaranteed to fetch the pivot row? And the insight here is that the only thing that we need to do is we generate predicates that evaluate the true based on the pivot row, because then we can use these predicates, for example, in the work clause or also in join clauses, and we know that they need to fetch the pivot row. And we do this using the following steps. We first randomly generate an expression to be used as a predicate. So, for example, the result based on the pivot, this null is not one. This node here returns true. Now we know that the expression, the predicate, should evaluate the true, which is why we can directly use it here in the work clause, or alternatively, it's fetched. But the question is, what if the expression does not evaluate the true? And in this case, we have a fix-up step where, when the predicate evaluates to false, we prepend this not operator, and if it evaluates to null, we append this is null operator. In which case, we can guarantee that afterwards the expression evaluates to true. But in terms of implementation effort, we believe that the literal evaluator is quite easy to implement, because it's simpler than, for example, programming language AST interpreters, which have to deal with mutable state. And we also expect that they're simpler than query engines, because we only need to evaluate basically literals. We'll consider a single row, while query engines need to consider multiple rows, some of them even concurrently. Furthermore, operators are implemented naively, because we found that the performance of the database management system is the bottleneck rather than our testing approach. So we didn't perform or implement any optimizations involved for testing functions like printf especially, and also other completers. So we believe that this approach is mainly useful to test the core functionality of a database management system, like comparisons and so on. Using this approach, we found about 100 bugs, almost 100 bugs, namely in SQLite, MySQL, and Postgres. And as I mentioned, this was the first approach that we actually came up with and implemented. The majority of the bugs that we found here were logic bugs, and actually quite a number of them could not have been found by NOREC and TiDB, because, as I said, PQS provides a ground truth in the sense that the operator semantics need to be re-implemented and compared against the database management system under test. And with that, I think we can again discuss PQS, and I'm happy to receive your questions.
So hello, folks on the call and from the audience. Do you have any questions?
Okay. Wait a few minutes. Okay. Since you have found so many bugs, I still wonder how the ideas come from, because we also test our TiDB for many years, but we don't think out good approaches to test such correctness the logical bugs. We always write cases by hand, yes, in unit test and other tests.
Yes, maybe related with my background. So I actually don't know much about database management systems. My main background is compilers and programming languages. Okay. And I think based on my background, I have a different angle on this problem, because you, for example, you know the database management systems very well. You know how they operate. You know maybe from your own experience what kind of bugs you might find in them. But I lacked basically the background, and maybe I started with a different approach than someone that has more knowledge on this in this domain could come up with. So maybe that might be a part of explanation.
Okay, then I can say it is think out of the box. Yes.
Thank you.
Okay, I have another question. Is what's the next plan of SQLite? Yes, since you have open source of it, and we also implement it by Golang.
That's an interesting question. So we want to go ahead and also test additional features, like come up with new approaches. It's still unclear what the best way to continue is. So we are basically still thinking about this. And in terms of implementation of a SQL answer, I guess the next step would be to also provide a sufficient testing of SQL answer itself, which is actually not that easy to implement, because we also want to check that SQL answer indeed like functions correctly, that no regression bugs can happen, so that SQL answer might omit detecting some bugs. So I think it's actually also an interesting question on how we can guarantee that our bug finding tool still works correctly or not. So I think that would also be something interesting.
Okay, got it. And I have another question. My question is too many. Okay. In our implementation of SQL answer, we found it's very hard to cover all the functions. It's too many functions to cover. So what do you think? Did the coverage, code coverage is important for SQL answer, or such for find logical bugs?
Yeah, so in my personal experience, I actually have to say that we found only a few bugs in the implementation of typically logic bugs. I think actually for finding logic bugs, it's not important to add support for functions. But of course, by implementing functions, you might still be able to detect some internal errors or crash bugs. So one strategy for implementation that in this case, like for NOREC and TLB, it would actually be feasible to, if the database management system provides a list of all functions that it supports, also indicating the number of arguments, maybe their types, and whether the function is variatic or not. It might also be feasible to just create a database management system for a list of all functions to then automatically test this using approaches like NOREC and TLB. And I think this is actually also supported by SQLsmith. So I think it also, at least for Postgres and so on, they query the database management system to determine a list of all bugs. Sorry, a list of all functions.
Okay, got it.
Okay, thanks.
Other questions?
Yeah, I have one. Hi, Manuel. Yeah, have you tried these approaches on data change statements like insert, delete, or update?
So basically, these kind of statements are issued in the first stage where we generate databases, but actually we didn't explicitly try to test these features. We found a few bugs related to them, namely when an update corrupts some data or insert.
Yeah.
But we haven't yet come up with an explicit testing approach for this. So I think this would also be an interesting thing to do.
Okay, thank you.
Hi, Manu. I have two questions. The first is, about how to build the expression on pivot row. As we know, each DBMS has its own dialect. Some of it treated none as special. For example, if an expression contains none, they directly evolve as a none. So the example you presented maybe not true for some of database. How do you solve this problem?
Okay, that's a very good observation. So as you just mentioned, this example actually doesn't work like this in, I think, most or all other database management systems. So the database and query generation part is specific to each database management system under test. So basically, we implemented the database generator and the query generator manually, and for each database management system that we wanted to test. But we believe that this actually doesn't require that much testing effort, I think a database generator and a query generator, I could typically need, I guess, at most 3 days to cover most of a database management system semantic. So I guess there is some manual implementation effort required, but the test oracles can then be implemented easier. But again, for PQS specifically, it's also required to study the SQL semantic of the database management system and test that the expression evaluator can be implemented correctly for it. So that's also a very good observation.
Okay, my second question is, I'm surprised that your example is pretty simple, and I think the schema and the dataset is important. It can help us to find more bugs, and how do you have any suggestion on how to generate this test data?
That's a very good insight. So we believe that, currently our database and query generation are quite naive. And I also believe that we might find some additional bugs by inserting some larger data sets. And actually, the scientific literature describes some approaches to do this. So it's basically important that we generate queries where the result set is not too large. Because you can, for example, imagine if we have a query that fetches all records from T0, T1, and T2, and if each of these tables has, let's say, 100 or 1,000 records, then the query will probably not terminate within 1 day or so. So, as I said, literature describes some approaches where we can still semi-randomly generate queries, but we can also ensure that they do not fetch too much data, that they actually terminate in reasonable time. And I think that would actually be an interesting next step to where we could generate more data based on this random query generation process.
Okay, thank you.
Okay, thanks.
So we also have a question from the chat window from Cai Xie, which is how to detect bug in run control.
Well, that might be interesting to also actually I've really discussed it also with some colleagues. This email read or so. Yeah, I guess for this, actually don't have back knowledge to give a good answer to this question. However, that it's important, but I guess probably I need to take more to give a meaningful answer here. But thanks for the suggestion, and I'll check it out.
Yeah, thank you. Any questions? Okay, so Dr. Manuel, please continue.
Okay, and thanks again for all the great questions. I really enjoyed discussing with you, and it's also great that you give me some ideas for further research. Sorry, I think. Yeah, so with that, I want to slowly start wrapping up. In today's presentation, I have presented 3 approaches to detecting logic bugs. So first NORAC, then TiDB, and now PQS. All 3 approaches are applicable to testing work clauses, but only TiDB allows comprehensively testing additional features. The main advantage of PQS is that it provides a ground truth, namely by re-implementing important operators in the testing tool itself. But this actually also means that the implementation effort of PQS is, for example, higher than for NORAC and TiDB. This was also pointed out by Cho-Chan. For example, if you want to test functions, then for PQS it might actually not be feasible to test quite a lot of them.